Welcome everyone to another seminar in mathematics and high energy physics at Physics Latam. Today we are happy to have Dmitrii Pirozhkov. He did his PhD at Columbia University. Then he went for a postdoc in ERC Synergy Grand Hyper K, working at University of Paris. Currently, he's doing a postdoc at Steklov Institute of Mathematics. His research field is focused on derived category of coherent shifts on algebraic varieties and their applications. Today, we will give us a nice introduction in essential algebraic tools for algebraic geometry. Thank you very much for accepting our invitation.
Okay, thank you very much for inviting me. I will speak about commutative algebra and its impact and its uses in algebraic geometry. So my talk is introductory and it's kind of some kind of preface to the mini course for algebraic geometry that will start on Monday, if I'm not mistaken. I'll try to approach the subject from a geometric point of view, because that's the point of view that will be most useful. Okay, so right. First, I want to say some words about what I mean by commutative algebra. So it's a study of commutative rings and modules over them. So for me, R will be a ring. When I say a ring, I mean associative, commutative, a ring that has a unit element that I will always denote just by one. I'll keep in mind what ring does this element belongs to. I'm interested in objects related to rings, such as modules. So a module is an abelian group together with an action of the ring R, such that those two structures are compatible. And I will also be interested in algebras over my ring. R prime is our algebra. Well, first definition is that if R prime is a ring plus compatible module structure over R. So it means that I can take elements of R and multiply any element of R prime by an element of R to get something that lives in R prime. And this is compatible with the multiplication in the ring. But also equivalently, since my rings all have as the unit element, this is just the same as saying that R prime is a ring and there is a map, which is a homomorphism of rings. In particular, it sends unit element to unit element. And the module structure appears by saying that if I have an element R here and an element R prime here, then their product is defined to be just take the image, let's say this is phi, the image of R small, which is now an element of R prime, and multiply it by R prime small. So those are three main definitions, and commutative algebra is a study of rings, modules over them, algebras over them, as well as various homomorphisms and properties of homomorphisms. For example, properties of homomorphisms of rings. So this is well defined and just algebraic definition of what kind of objects we study and what do we do with them. And what I want to do is to somewhat motivate why do we see something like this if we try to think about algebraic geometry or just something geometric. So it's motivation for commutative algebra. This won't be very formal. It's just some explanation for why these objects have something to do with geometry. So one thing that people started doing a long time ago in mathematics is to study polynomial equations. For example, a very well-known equation, x squared plus y squared equals 1. If you draw the graph of this equation on the real plane, you will see a unit circle. But this describes solutions in real numbers. But you can also try to take this equation and look at its solution in various other rings. For example, solutions, you can look at solutions over Q, over rational numbers. And you will see that if you have a pair of rational number a divided by c, b divided by c, where I put them to the common denominator, is a solution. If and only if a squared plus b squared equals c squared. So those are called Pythagorean triples, and they appear in many different aspects of mathematics. And this perhaps illustrates the idea that sometimes having a single equation and studying its solution over two different, let's say, fields, over a field of rational number, over a field of real number, maybe also complex solutions, why studying the equation itself is a useful thing to do if you want to apply it in several different contexts. So what can we do along this idea? Well, we can look at, start with a ring R and take a system of polynomial equations with some kind of set of variables I. This goes through some set. And polynomial equations, let's say they will be fj, where j goes through some other set with coefficients in R. So for example, the equation I wrote here is just a single equation with integer coefficients. In fact, all coefficients are actually equal to 1, or maybe -1 if you want a standard way to say that an equation is something equals to 0. So this is an example, a very classical object that people study in mathematics. And one can observe that this system of polynomial equations, you can look at a certain universal object associated to it. So there is a universal object, which is, we take the ring R, we add all those ti's as just formal variables, and then we take a quotient of this ring by the ideal generated by all equations. So this is kind of a universal ring in which the system of polynomial equations has a solution. Because if you just take all those ti's, then by definition of the quotient ring, they satisfy the equation. Because when we plug them into an equation fj, we get something that lies in this ideal by definition. And so it is 0 in the quotient ring. Now, what I want to also say is that over here, if you think of a system of polynomial equations, we can also think about solutions of this system. Just a moment. Solutions in our algebra called L. So those are just sets of different elements of L numbered by this set large I, so that those elements satisfy each polynomial equation that we have when we plug those values into the equations. And in terms of this universal object, it is easy to see that this corresponds to homomorphisms of our algebras from this universal quotient to L, where the association is that we take a solution and we send the variable ti to the corresponding element of the ring L. So, and now in this point of view, you see that you don't really need to know the variables ti that you have. You don't really need to know what exactly system of equations do you need. You can just study some kind of R algebra here. And then just look at homomorphisms of R algebras from your R algebra to arbitrary given algebra L. And on the one hand, this describes exactly what happens when you say you want to study solutions of systems of polynomial equations, assuming that you want solutions not only in the ring R itself, but also in some other rings, like in the example that I had above, where we had an equation with integer coefficients, but we looked at solutions in rational numbers or solutions in real numbers. So if you want to do this, what you're doing is essentially just studying some kind of algebra and studying sets of homomorphisms from that algebra to a ring. Okay, so this leads to a definition, or maybe just a notation. So if A is an R algebra, then I say an L point of A is just defined to be is a choice of homomorphism A to L of R algebras. And also a point is geometric, is called geometric. If L happens to be a field. So far, this is just a terminology. I have renamed homomorphisms of algebras to be points, but we will soon see that this definition is at least somewhat reasonable, and it is useful for thinking about commutative algebra problem geometry. So so note that if we have this R algebra A and we have some other algebra L, then an L point, well, it's a homomorphism from A to L, but any homomorphism can be decomposed into, first you take the quotient by the kernel, and then you take an embedding of this image of phi, this part is also equal to the image of phi by the first homomorphism theorem about rings. When we study all L points, one thing that we can do is first to study what are possible kernels of homomorphisms from A to some other algebra, because this is something that only depends on A, and this is intrinsic, does not depend on the choice of the auxiliary algebra L. And then afterwards we can study embeddings into L, but that's now not really related to what A was. So we can study the kernels, and the kernel is always an ideal of the ring A. And if a point is geometric, then it's not hard to see that this kernel is a prime ideal, which means that if x times y lies in the kernel, then either x or y lies in the kernel. Okay, so we can, if we want to study points of our algebras, we are led to the study of ideals inside of A, or for many purposes, it is useful to think of prime ideals first and foremost. And this is to a definition that a spectrum like A is the set of prime ideals. A. Okay, so now I want to say a few words about this notion and its relevance. Okay, so one thing that's so as I said above, since any geometric point corresponds to a choice of a prime ideal, and then an embedding of the quotient by this ideal to L, then the study of the set of prime ideals is relevant to the question of what kind of geometric points do we have in A. And one extremely important property of this notion of the spectrum is the fact that it actually has a topology. Or rather, first I want to say that there is a certain approach that if you have some element f in your ring A, then you can think of it as a function. Kind of function on this spec A by saying that on a prime ideal in A, the value of f is its class in the quotient ring A modulo this prime ideal. So it's a very strange notion of a function. At any point, you have some result, which is something that functions do. But on various points on different prime ideals, you get elements of just different rings, a modulo 1 prime ideal, a modulo 2nd prime ideal, and so on. So that's not extremely similar to a function as seen in analysis, but it happens to be a very nice way to think. And if you want to get a better intuition about this approach, or including some pictures, I think a good reference for this philosophy, reference for this point of view, just one reference among many, but the one that I like a lot, it's a set of notes by Yuri Manin that's called Introduction to the Theory of Schemes. It's a short book, and if you look at first 20, maybe 30 pages, you will see how Yuri Manin, who has postulated here, how he introduces the idea of commutative algebra as a way to work with systems of polynomial equations, and how this way of thinking leads to the definition of spectrum, how it leads to the idea that elements of the ring should be thought of as functions on the spectrum, and various properties of those things. And he includes geometric interpretation as well. And I think this book you can find it in Google. Not sure how legal it is, but it is freely available. Okay. Right. So note.
Sorry, there's a question in the chat.
Okay. Just a moment. Spectrum of a ring and the spectrum of an operator. So if it is an operator on a finite dimensional vector space, if V is finite dimensional and you have, let's say, a linear map from V to V, so an operator, then this gives you a way to think of V as a module over a polynomial ring over K of X, where K is the base field, where X acts by phi. Then you don't really get the spectrum of the operator as a spectrum of this ring, but it's something very similar. It's the support of this module as a subset of the spectrum of the ring. So, but if it is infinite dimensional, then I think the notions of spectra for operators are more complicated, and there are less relations between them. But I think this was one of the original motivations for this introduction. Okay, and the other question is, if the point is geometric, then L is a field, but the kernel is prime ideal, why not maximal ideal? So mostly this okay, what I want to say is that when I defined a point as a map from A to L, as I've seen in the decomposition, I can restrict my point of view only if I only look at points where the homomorphism of algebras is surjective, then I only lose the information on how this quotient by the kernel embeds into L and nothing else. I can look only, in this case, I can only look at maximal ideals. In this way, if I want to think of geometric points, I can say, for example, that a point of geometric if the map is surjective and the kernel is maximal ideal. In general, even if the quotient of A by the kernel is something like Z, like the integers, I still want to think of this as a geometric point. Sorry, I guess I didn't answer the question, but we will see later why prime ideals are important to this point of view. And just now, I'll just say that I'll just only say that the quotient of A by the prime ideal is a ring that has no zero divisors. So this quotient naturally embeds into its ring of fractions, which is a field. So each prime ideal naturally gives us a geometric point in the definition that I gave, because we take a map from A to this ring of fractions as a composition. First we project the quotient and then we embed it to the ring of fractions. I want to say that if we ask the kernel to be maximal ideal, we'll just get a different set of points, and we want the ones corresponding to the prime ideals. Okay, so now I wanted to say effect that the definition of this point of view of thinking of elements of the ring as functions has one strange property that if we take an element, this actually can define a zero function even if f is not equal to 0. For example, if f is nilpotent, which I'll remind by definition means that there exists some integer such that f raised to z power is equal to 0 in A. Then f lies in P for all prime ideals. And when I say for all prime ideals, I will write for all P in the spectrum of the ring, because that's just my definition of the spectrum of the ring. Hence, if you think of f as a function, then it defines a zero function everywhere. Another fact is that this actually is the only option if f lies in the intersection of all prime ideals. Then f is nilpotent. So this is an exercise in commutative algebra, and just for the sake of completeness, let me briefly indicate of how it works. Let's prove this. If F is not nilpotent, consider the set of all ideals I in the ring which do not contain any power of F. Note that since F is not nilpotent, no power of F is equal to 0. So this set is of ideals is non-empty, since the 0 ideal works. This is a partially ordered set by inclusion. And you can take unions of ideals that of any chain of embedded ideals. So by Zorn's lemma, there exists a maximal element of that set, which is some ideal I ideal has no powers of F, and it is maximal with that property for any element, let's say H. The ideal generated by I and H has some power of F. What I want to say to prove my statement is that this ideal I that I have found, that it will be prime, so that if F is not nilpotent, I will find a prime ideal that does not contain F because it contains no powers of F at all. So assume, we'll prove this by contradiction, assume I not prime. By definition, this means that there exists two elements of my ring, so that H times G lies in the ideal, but neither H lies in the ideal nor G lies in the ideal. So by the maximality, for some n, for some power, for some n, we know that Fn lies in I plus H. In other words, F to the power n is equal to some element of the ideal I plus A1 times H. And similarly, F to some power m is equal to I prime plus A. Yeah, sorry, this should not be A1. This should be just A. And there is this. A primes times G. Hence, Fn times Fm is equal to I times I prime plus I times A prime G plus I prime times A H plus A E prime times HG. But now this part lies in the ideal I. This part lies in the ideal I. This part lives there as well. And here, since we know that HG belongs to the ideal, we know that this also is an element of the ideal, but this is a contradiction, since we have assumed that no power of f lies in I, but here we have constructed an explicit power that is an element contradiction. So this means that the ideal I that we have constructed over here will be prime, and then any non-nilpotent element of a ring lives in some prime ideal. Okay, so yeah, okay, so this is an important property of prime ideals, but also note that incidentally, we have not said that explicitly, but this also proves that the spectrum of A is always non-empty if the ring is not just zero. Because if the ring is not zero, then we have at least the unit element, which will not be nilpotent. And by the proof here, by Zorn's lemma, we will have constructed at least a prime ideal, or in that case, it will become a maximal ideal, essentially by definition. Okay. So, right. Now, I want to say that this set has a topology. The risky topology on spec A. So the idea is natural if you take into account this point of view that element of the ring should provide functions of the spectrum. What we want for any reasonable topology is that if you have a function, then the set where it vanishes should be closed. And we essentially define the topology by this idea. So we say that a set Z in spec A is defined to be closed if we can find some set of elements of our ring such that that is the intersection. It's a set of points where all the functions vanish. So it's kind of an intersection of the equations fi equals 0, or in more down to earth terms, this just means a set of prime ideals such that fi, such that for any index I, the element fi belongs to this prime ideal. So and this defines closed sets, and you define, as usual, open sets are complements to closed sets. And it is an exercise to check that this defines a topology. So the key question is that closed sets should be that an intersection of an arbitrary family of closed sets should be still closed, which is kind of trivial because if you look at this definition over here, if you just take the equations for each closed set and take a union of the equations, you will get the intersection. But then we also need to show that the union of finitely many closed sets is always closed, and that's an exercise. So right. So this is exercise, and now we can look at an example let's say we have a ring that's a ring of polynomials over complex numbers as a C algebra. Though that's not important for it's not important that I consider this as an algebra over complex numbers for the rest. So what are prime ideals of A? So well, first of all, if f is an irreducible polynomial, then f is a prime ideal. But since we work here over complex numbers, so the only thing that we have only linear terms. And any linear term by up to scalar multiplication, it can be written as x minus lambda, define prime ideals. Sorry, this is not only then, but if and only if. Define prime ideals, which all are maximal. But also, there is another option. What if we don't have any polynomials at all, and consider just a zero ideal, which is a prime ideal because this ring has no zero divisors. Yeah, sorry. What I meant above was that if you have any ideal of this ring, since you can divide polynomials with a remainder, you know that any ideal is generated by a single polynomial, and it will be prime if and only if the polynomial was irreducible, which in this case means it is linear. So geometrically, you have complex plane where each point is a number lambda, which defines the maximal ideal x minus lambda. And there is also something over here that's the ideal zero. And if you look at the topology we have defined, since closed sets are defined by vanishing of some functions in the quotient ring. So if I have f over here, then it vanishes at the zero ideal, if and only if, by definition, f becomes the class of f becomes zero in the quotient by this ideal. So if and only if f is actually a zero polynomial. So any non-zero function does not vanish in this fat point that I have drawn, called zero. And so, in other words, this lives in any open subset. Well, non-empty. So it's kind of slightly strange space where you took all points of the complex plane, added one strange point, and glued it to all points together. This is what happens when you look at polynomials in one variable. But if you take, for example, C of xy, you get something more complicated. So, of course, we still have for any So for any pair of complex numbers, we can make a maximal ideal that's generated by this expression. Well, we also still have the zero ideal, which is also prime. But also, if f is some irreducible polynomial, for example, the polynomial that I have started the talk with, x squared plus y squared equals 1. So this is an example. Then f is also a prime ideal. So what you get is in even more bizarre space. You have c squared of points corresponding to maximal ideals that I have drawn over here. You have a fat point corresponding to the zero ideal. And then you have a bunch of ideals corresponding to irreducible polynomials into variables. So those are kind of correspond to curves. Algebraic curves in C squared. And there is some kind of topology between all this. So, all right. What I want to say? Yeah, and also I want to just give a definition that if you have an element of the ring, I will define df a distinguished open subset. Spec A corresponding to this element f is defined to be a set of prime ideals in the spectrum that do not contain f. And you can check that this is an open subset because it's exactly the complement to the set of all prime ideals which contain f. Such dfs form a basis of topology. In other words, any open set, open subset of the spectrum is a union of several distinguished open subsets. Those distinguished open subsets are just some kind of notion of a nice, understandable neighborhood of a point in this spectrum. And there was a question in the chat whether this set of ideals constitutes a manifold too in the last example. So not really, I would say it's because it contains polynomials of many different degrees. So you may look at all irreducible polynomials of fixed degree into variables. And then, yes, there is a reasonable way to think of this set as a manifold, or rather an algebraic variety that you will study starting from next week. But it's something like a countable union of manifolds, if you wish. Yeah. Okay. So why are we interested in this topology? Because what we want to do with this picture and what we want to do in algebraic geometry is to work log. So I would say this is another part. So Y topology. Well, we want to work locally on this spectrum. I will explain what this means, but first, unfortunately, I will need some algebraic preliminaries. To start with the ring A. For the purpose of this part, you don't really need it to be an algebra over something else. You can just work with the ring. Let's say some subset of A, I will call it a multiplicative subset. This means that for me, this will mean that the unit element lies in S, and if I have S1, S2 in this set, then their product is also an element of this subset. So two main examples that you can keep in mind, but it's often easier to just use the definition than keep track of the examples. So there are two examples. First, if you have some element f in A, then the set of powers of f is a multiplicative subset. But also, if you have a prime ideal in A, then the set, the complement, so all elements of the ring that do not lie in the prime ideal, forms a multiplicative subset. Note that the element 1 does not lie in the prime ideal by definition, because it's not a proper ideal if it contains the unit. Okay, so we define a localization of A in this subset, and we denote it as S-1A to be a ring formed by a ring of fractions of the that look like A divided by S, where A is an arbitrary element of the ring and S small is an arbitrary element of this multiplicative subset. Modulo the equivalence that AS is equivalent to B divided by S prime, if and only if there exists some U in this S, so that U times AS prime minus BS is equal to 0. So I claim that what I have defined here is an equivalence relation, and this is of course necessary. And then I also claim that, and I leave this as an exercise. Yeah. So exercise is to show that this relation that I have shown is transitive, and the usual rules for addition or multiplication of fractions is well defined. So note that by definition we have a map from A to this S-1 of A, which sends an element A to the fraction A divided by 1. Recall that I have asked for the unit element to be part of S, so it can be taken as a denominator over here. So this was node 1, and node 2 is that so if you look at this definition, you may consider it a bit strange that we rely on this this extra element U in the set, but that's necessary. U is necessary to avoid division by 0. In the sense that if we can find some element A and element S of our multiplicative subset so that this product is 0 in A, then to have then we need 1 divided by S to be 0. Otherwise, 1 divided by S is equal to A divided by AS is equal to A divided by 0. This is strange. So you can check that the definition that I gave ensures that if you have an element A small of your ring that is a 0 divisor and can be multiplied by something from the multiplicative system to get 0, then it is sent to 0. Okay, so all right. So and another exercise. Yeah, I think I will just do this exercise as well. So if you have this map over here, then let's say phi, then the kernel of phi is exactly the set of elements of the ring, such that there exists some S in S, so that A times S equal to 0. Yeah, okay, I've said that I will solve this, so let's do this. Solution. So what is the kernel of phi? It's a set of all elements A, so that A divided by 1 is the 0 element in this localization S-1 A. In other words, this A divided by 1 should be equivalent to 0 divided by 1, which by definition means that there exists some S in the multiplicative subset, so that S times A times 1 minus 1 times 0, which is clearly just A S times A, should be 0. This is the definition of the equivalence relation, and this gives you the kernel. So what I need is a lemma that prime ideals. How do prime ideals behave when you do this localization procedure? Prime ideals of this localized ring are exactly the same thing as prime ideals of A, which do not intersect our multiplicative subset. So before I will prove this lemma, I will just give a corollary. So suppose we have an element f, and we consider the multiplicative subset consisting of its powers as above. Then we define it's for simplicity of notation, a with a lower index f is defined to be s minus 1a for this multiplicative system, and its prime ideals. Sorry, this is a ring, and the spectrum of this ring by the lemma above, it's exactly the set of prime ideals in A that do not contain any power of f. But since a prime ideal contains a power of an element, if and only if it contains the element itself, this is the set of prime ideals in primes in the spectrum of A, such that f does not lie in P. And this is the definition that we have just recently seen as the definition for the distinguished open subset of the spectrum. So this was also equal to df. In other words, by using this localization procedure, we have taken our basic distinguished open sets, and we have interpreted them as spectra of various rings related to our original ring. And in fact, one can check that, since this part here is the spectrum, it has the Zariski topology as we defined using the ring structure. Since df is an open subset of spectrum of A, it also has the induced topology, just as open subset of a topological space. So in fact, this is not just a bijection, but a homeomorphism. So we started with the ring. We have constructed some kind of geometric object that we have called spectrum, which was just a set of prime ideals with some topology. But then we saw that at least some open subsets of this topological space they're not just topological things, they actually correspond to a very precise and very common algebraic structure. Distinguished opens, they come from algebra in some sense, or that you can interpret them in this algebraic way as spectra of the localizations. It's just a very useful point of view. Okay, so what I want to do, I wanted to prove the lemma, or at least to indicate the proof for understanding how the prime ideals of the localized ring look like, because that's an important argument that is fundamental to working locally, for proving things locally. If you have something about the ring that you can interpret as a statement about its spectrum, then sometimes instead of proving it for the ring itself, you can just cover the spectrum by distinguished open sets and do the proof over each open subset, essentially by replacing your ring with this localization. which sometimes makes things easier. So, okay, yeah, I wanted to give a proof of lemma. So, so if you have a P with index S, let's say in the localized string a prime ideal, I can ascend it to a set of numerators. Since by definition, all elements of the fraction of this localized string can be represented as fractions, something divided by something from the multiplicative system, it makes sense to speak of numerators of fractions. And a numerator of an element in S. So set of numerators, which will be a subset of A. So there are some questions about how well defined it is, but note that if you have A divided by S over here, then you can say that its numerator is A, but also this can be written as A S prime as S prime, then you would get A S prime. So it seems that the notion of the numerator is not well defined, but since we are looking at the set of all possible numerators, we just take all of them, and this gives a well-defined set of subset of A. And in fact, this is a prime ideal. So why is this true? Well, first of all, we need to show that it is an ideal. If we have some A is a numerator of A divided by S that lies in P S, then for any A prime and A times A prime is of course a numerator of A prime times A divided by S, which is A prime divided by 1 times A divided by S. So this also lives in the ideal PS. So this shows that the set that we get is closed under multiplication by arbitrary elements of the ring A. So additivity in the sense that a sum of two numerators will also be a numerator follows by the fact that if A divided by S lies in PS, then A divided by 1 is equal to S divided by 1 by S also is in PS. So if you have A and A prime and they're both numerators, then A divided by 1 and A prime divided by 1 are also elements of PS. And so their sum will be A plus A prime divided by 1. Hence, closed under sums. Now we need to check that it is prime. If A times A prime is a numerator, this means that A times A prime divided by something lives in our prime ideal PS. Then we can write it as A divided by 1, A prime divided by S lives in the PS. So by the fact that PS is prime, we get that either A divided by 1 or A prime divided by S. Sorry, Mila lives, but lies. PS. And hence the numerator of one of these two fractions will also lie in our set of numerators. So this shows that we started with a prime ideal in the localized ring, and we have constructed, by looking at all possible numerators, a prime ideal in A. And note that this is not just a prime ideal, but also it does not contain it does not intersect this multiplicative subset. Since if we had some fraction where both the numerator and denominator lived in S, we could invert it and get the unit element of the ring by multiplication. And we know that this is impossible in PS. So this is a correspondence in one direction, and I leave it up to you to check that this is actually a bijection between the set of prime ideals in the localized ring and prime ideals in A, which do not intersect S. Okay, so having done this lemma, we have confirmed that those distinguished open sets they correspond to certain algebraic procedure. And to say more about what it means to work locally, I'll just say that can also localize modules and algebras. Over A. And the definition is the same. If you had a module M, then we define S minus 1 M, where S is still a multiplicative subset of A. As a set of fractions, M divided by S, a similar equivalence relation, well, same equivalence relation. MS M prime S prime if there exists some U in S, so that U times S prime M minus S M prime is equal to 0. This is you can check that this is well defined. This defines a module structure over the localized ring, and it is a fact that the assignment from M to this localized module is an exact functor, which means that if you have some map of modules, then if you take the kernel of phi and localize it, you get the same as the kernel of, I will write S minus 1 phi, where this is the induced map for localized modules, defined naturally on these fractions. And the same for co-kernel. So to illustrate what it means to work locally, let me prove the following lemma. So illustration. So suppose we have ring A, module, then the module is actually 0 if and only if there exists an open cover of the spectrum by this distinguished open sets such that the localization of the module with respect to multiplicative system formed by powers of Fi is 0 for all I. And geometrically, what happens is that we had spec A, and module was something as associated with the string. So we have found an open cover. So we can check that M is 0 over A, but instead we can look at spec of the localized string, which is isomorphic to dfi, and induced module over AFI is 0 on all sets from the cover. So this may sound a little bit stupid, just checking that the module is 0, but it becomes more useful if you think, for example, that this M is some kind of quotient of two maybe constructions that you did, and you want to check that they're the same, and you interpret this as showing that the quotient is 0, and then instead of checking that the result is 0 for an arbitrary ring A, instead you can look at, you can cover its spectrum by the strings that may, for some reason, be easier for you to handle, and check the property only on each distinguished open subset. And this is the fact that there are many properties of modules that you can check locally in the sense is very important for algebraic geometry, because there, instead of just strings and their spectra, you work with more global objects. And I won't say more about those global objects because that will be a topic for future talks. Okay, so let me prove this. So pick some. So first of all, one direction is obvious, of course. If the module is 0, then by the definition that I gave, the localization of the module with respect to any multiplicative system is, of course, also a 0 module. So we only need to show that if you have some element M in this module, which is non-zero, we want to show that there will be at least one distinguished open subset from the open cover over which the corresponding localized module will be non-zero. the element m divided by 1 in the localized module is not 0. Okay, so since to do this, let's first consider the annihilator set of this element, which is by definition just the set of elements of the ring, so that when you act by the element of the ring on this M, you get 0 in the module. This is you can easily see that this is an ideal, and moreover, since M was not assumed to be a 0 element, this means that not everything in our ring kills it, because our ring has a unit element, so at least the unit element is not an element of this annihilator. So now we can consider some P, which is a prime ideal containing annihilator. So it exists by the same variant of the Zorn's lemma that we discussed. We can just look at all ideals containing this annihilator. We know that at least there is at least one proper ideal, which is the annihilator itself, and to look at chains of increasing ideals and take the maximal among them, and it will actually be a maximal ideal, not a prime ideal, but why not? Now we can pick some Fi, which does not. So Fi's were elements of the ring, and we think of them as functions on the spectrum. So we say which does not vanish on P as a point in the spectrum. In other words, Fi does not belong to this prime ideal. This exists because we have assumed that the set of distinguished open subsets DFI is actually a cover of the spectrum. So in particular, there is at least one element Fi whose distinguished open subset contains the point P. And if you uncover the definition, you will see that this means exactly that Fi does not belong to the prime ideal. So if you pick such Fi, then I claim that M divided by 1 is not equivalent to 0 divided by 1 in a Fi. Otherwise, by definition, that would mean there is some power, say that Fi to the n times M is equal to 0 in the module. But we have assumed that Fi doesn't lie in the prime ideal containing the annihilator. This implies that any power of F is not contained in this ideal, but then none of the powers annihilate our element. So this would contradiction with the fact that annihilator of M lies in this prime ideal. So we can check that a module is non-zero by looking at its various localizations, assuming that we have this topological condition that the distinguished open subsets corresponding to the elements that we localize in actually cover the entire spectrum, and they don't omit any points. Okay, so So this is something very useful, and but what we can also do is we can instead of looking at distinguished open subsets, we can work kind of near points of spec A. So so we have some point P here. Then, as I've mentioned briefly above, we can look at the multiplicative system, which is formed by all elements of the ring that do not lie in this prime ideal. Note that one of the ways to think of this multiplicative system, it's a union of those basic multiplicative systems that we have discussed above for all f which do not lie in the prime ideal, or in terms of in the language of functions, for all functions that do not vanish at this point. So you can think of this multiplicative system as a union, something common for all distinguished open sets containing P. Then we also define the shorthand notation AP as a localization in this multiplicative system. Similarly, MP for modules and so on. Note, we always have a map from A to the localization, so there is a map like this, and one can check that any map of rings defines a map of spectra in the other direction by taking a prime ideal of the codomain and taking its pre-image. So this map always exists. In the previous case, where we localized in powers of some function f, we had an embedding of an open distinguished subset, but this is usually not open, not an open embedding. But it's still at least an inclusion of sets, because as we discussed above, we have discussed we have proved the lemma about prime ideals in a localization under arbitrary multiplicative system. So this is the set of prime ideals, let's say Q, in spec A, such that by definition, we said that it's a set of prime ideals which do not intersect our multiplicative system, and our multiplicative system is a complement to P in A. Thus, we can think of this as if Q does not intersect the complement to P, this means that Q is actually contained inside of the prime ideal P. So this is still a subset of the spectrum of A, but it will not be open usually. Okay, so you can interpret this note above here about the union of all powers for all elements that do not intersect P as the following exercise, that spec AP as a subset, spec A is the intersection of all distinguished distinguished open subsets of A containing the point P. Yes, there was a question. If you have any questions about the seminar, you can send them, for example, to me. I can. So my email address is Pirozhkov at EMJ.R. And I'll be glad to answer the questions. Sorry, open subsets of the spectrum of A. Sorry, yes. Thank you. So we have some subset of spectrum, and I claim that this subset is an intersection of all opens that contain the point P. Okay, so what I want to say, yeah, and also an addendum to the lemma about the module M. The vanishing of the module M is also equivalent to the fact that its localization in all prime ideals is 0 for all points of the spectrum. So you can check that the module is 0 by looking at all points of the spectrum and by looking at the local version of your module corresponding to this point. And proof is omitted because it's the same. So this is another way in which you can work locally. If you want to check some properties, sometimes you can look at all prime ideals and localize in those prime ideals and consider your algebraic question there. And one possible benefit if it takes this AP, it's actually it is a local ring in the sense that it has a unique maximal ideal. That's not very surprising if you look back at the definition, at the explanation of the spectrum that I had over here. Since it's a set of prime ideals of A which are contained in P, then clearly the best and the maximum possible ideal like this is just P sub. So if you are doing some algebraic questions that are easier to study for local rings, you can use some similar approach to reduce many questions to just properties of local rings and what happens for modules over them. That's not remark, I guess that's the definition, but it's not a very strict definition. It says that a property of a module or map of modules, or algebras, or map of algebras, over our ring A is called a local property. If it holds over A, if and only if it holds for localized situations, over all prime ideals in the spectrum. And so far, that's just a definition. It just means that it is something that you can, instead of checking over the entire ring, you can check only for those local rings associated to A. And just as an exercise, let's say if I have a map from M to N of A modules, then being injective or surjective is a local property. So if you want to check that the map is injective, you can instead look at each local ring and check the injectivity there. And the proof, the idea of the proof is similar to the lemma about vanishing that I have demonstrated. You can just use the definition of localization, and you use the fact that you cover all prime ideals, and you conclude that everything works as you want. So, okay. So, one remark is that so many notions are local in the sense that instead of defining them, they hold over a ring, even only if they hold over all, let's say, distinguished open subsets of that ring, or as localizations on all prime ideals. This theoretically, at least, this allows some kind of globalization or gluing different spectra together into some other kind of objects. And this is actually what happens when you define a scheme. And I think starting from the next week, you will see something like this. That entirely due to the fact that many things are local, those notions can be translated to this more global version where you don't specifically need to work over some fixed string. You just need to kind of know that you have a bunch of local conditions that are all conditions about rings and modules, and this will make sense. Okay, so and another remark is that there are so this notion of locality does not give you kind of everything that you would have wanted if you come from the study of the usual manifolds. For example, locality can is sometimes tricky, and here I will say what I mean. That if you look at, let's say, a curve that's defined by the equation y squared equals x cubed plus 1. Looks something like this. And let's say this point here is called P. No Zariski open neighborhood P looks like a fine line. So for usual smooth topological manifolds, you have the, in fact, even the definition says that any point has a neighborhood that's isomorphic or diffeomorphic to some open subset of just Rn of the basic case. But in algebraic geometry, if you use this Zariski topology, sometimes this is just not true. That this point P over here, its neighborhoods don't really look like neighborhoods of point on an affine line. It is a little bit tricky to prove or even to say exactly what this means. But somehow this those Zariski open sets, they're too large, and localization at a prime ideal is sometimes it also doesn't look like what happens in topology. So but this can be fixed, can be kind of fixed with more complicated notions of more complicated notions of neighborhoods. So I write neighborhoods in quote marks because usually you don't just define a different topology on the same set of prime ideals. And in fact, it's some approaches like étale topology, you don't really have any topological spaces. You have to introduce something new, and it is sometimes quite painful to work with those generalized notions, but they exist. So if you want to work with algebraic varieties and say operate in this manner where you expect that every point has a very simple neighborhood that looks like a neighborhood in the affine space, you can, but you have to pay the price of using a very complicated and highly theoretical notion of neighborhoods that I will not speak about. But that's also an important thing to keep in mind, at least as the fact that you don't have neighborhoods which are isomorphic to open subsets of a different curve is important. Okay, so I guess I have 15 minutes, so I want to say that sometimes I have spoke at length about this notion of locality because it's a key that allows us to use commutative algebra as a basic case of algebraic geometry and reduce global geometric questions to kind of local questions about rings. And I will continue this topic, this theme, by saying a few words about how we can sometimes go from this localization at the complement to the prime ideal was somehow some kind of it wasn't really a neighborhood of the point as I've mentioned, because as I mentioned here, I said here that it's an intersection of all open subsets containing this point, and the intersection of infinitely many open subsets in the topological space is usually not open. but at least you can think of this as some kind of very small pseudo neighborhood of the point P. Sometimes you can actually work in at points, not just near points. So what I mean here is that if you have P in the spec A, then instead of the localization, you also have a map from A to A modulo P. So just take the quotient by this prime ideal. Similarly, if you have a module, you can make a module M modulo P as usual. And it would be often very nice if the commutative algebra question that you want to study for your module or for your ring can instead be reduced to various simple rings like quotients by the prime ideals, at least because quotients by prime ideals don't have any zero divisors, and rings without zero divisors are often nicer than the general case. But this is less automatic. What do I want to say? Yeah, I want to say an example statement where you can check everything just on the quotients instead of localizations. So it's a statement that's sometimes called Nakayama's lemma. Now the problem is there are many different ways to say what exactly. There are many essentially equivalent formulations and formulations that are not maybe equivalent but are proved in exactly the same way. And I'll say a couple of statements. So first, let's say, suppose you have prime ideal, and you have a map of two modules, map of A modules. And M is a finitely generated module, which means that there exists a finite set of elements, so that the smallest module that contains them is actually M itself. And assume that the induced map M modulo Pm to M modulo Pn is surjective. Then there exists some element of the ring that actually lies in a shift of the ideal. So what I mean is that modulo Pf is equal to 1. The residue class of F is equal to the residue class of the unit element. In particular, F does not lie in the prime ideal because 1 is not equal to 0. Such that the localization, the map of localizations is also surjective. So geometrically, this means that if you have this point P, and you have two somethings, something called M, M, and something called N, Pn. and the map between them is a surjection, then under some finiteness conditions that M is finitely generated, you conclude that there exists some distinguished open set df. Note that df will contain P because F does not lie in P. Such that if you look at modules, corresponding modules over this thing, let's say this will be MF. And this will be MF. That the map between them will also be surjective. So you have checked something at exactly a single point and not even in the small neighborhood of this point, but at the point itself, and concluded that you can find some neighborhood, some open, some distinguished open set over which the map is still surjective. And so this was one version that is closely aligned to the way I structured my talk, but there are other versions. For example, the classic and simple version is that if M is finitely generated module and A is local, if you can get module, recall that local ring is the one with the single, with a unique maximal ideal, and if multiplication by this ideal doesn't produce a strict, a proper submodule of M, but instead M itself, then you can conclude that M is equal to 0. So, and to go from the second formulation to the first, you look at the co-kernel of the map from M to N. That's defined globally. That's something defined of the whole ring A. And if you look at this co-kernel as a module, you look at its localization at the point P, you gradually check that if the map of quotients is surjective, then this condition holds for the co-kernel. So the co-kernel will be 0 in the localization, and then you can check that the co-kernel will be 0 at some distinguished open set. So I don't really have a lot of time to discuss this, so I think it will be clearer if I just give a reference. Note that actually it's kind of a remark which I found a little bit funny, that if you look at Stek's project tag 07RC, has 12 variations of Nakayama's lemma. So including both of those that I have mentioned here. So and it also has very brief proofs, but you may prefer reading some more readable reference. For example, a very good book is A.T.M. McDonald's Commutative Algebra. It will have more details about localizations and this whole process of working locally, even though it will be mostly in the form of exercises. And this book is, I would say, it uses a more algebraic point of view and does not force this idea that working locally on the spectrum using the fact that the spectrum has a topology and open sets and points is useful. But still a very good book, and I recommend it. I wanted to speak about some other topics, mostly starting from Nakayama's lemma about these conditions that the module should be finitely generated and various conditions that you put on rings or map of rings that play very nicely with these notions, like being a Noetherian, finitely presented. But since I don't have time, I guess you cannot really expect to fit everything about commutative algebra into a single talk of 2 hours. So I hope that I have at least motivated this process of localization and shown some applications for topology on the spectrum and how it clarifies, or at least gives you some platform to stand on and to imagine geometric approaches to algebraic questions. I guess that's all, and I would be happy to answer your questions here.